Hi, this is Lance from LangChain. I'm going to be talking about retrieval and long context LLMs and a new method called Raptor. So over the last few weeks, there's been a lot of talk about is RAG dead with the advent of new long context LLMs like Gemini, 1 million tokens, Claude 3 now with up to 1 million tokens. It's an interesting question. I've recently been using long context LLMs for certain projects. Like, for example, this code assistant that I put out last week basically used a long context LLM to answer coding questions about our docs on LangChain expression language. I'll kind of zoom in here so you can see it. So these are around 60,000 tokens of context. We take the question, we take the docs, we produce an answer. And this is really nice. No retrieval required, just context stuff, all these docs, and perform answer generation directly. So I'm a big fan of using long context LLMs in this way. But there are some considerations I wanted to kind of point out here. So I ran evaluations, and for those evaluations, I look at 20 questions. So basically it's 20 generations. Now look here, so this is the Langsmith dashboard that I used for those evals. And you can see something kind of interesting. The P50 latency tells you the 50th percentile latency for each of those generations. So again, remember there's 20. So it's around 35 to 46 seconds depending on the trial. This is on the same data set, same 20 questions. There's some variance run to run, so that's kind of expected. And again, the P99, it's up to 420 seconds. That's really long in that case. But maybe more interestingly, if you look at the cost, again, there's 20 questions. So the cost is ranging from maybe like $1 to, $1.30 per generation. So, cost and latency are things to think about when you're talking about using really long context LLMs, as opposed to like a RAG system where you're performing retrieval of much smaller, more directed chunks to your question. Now, the other thing that came up is a lot of people asked, hey, can you swap this out and use a local LLM? And my go-to local LLM is Mistral 7B v2, which actually has a 32,000 token context window, but that's still a little bit big relative to my docs, which are around 60,000 tokens. So, I couldn't just context stuff them as I did here. So these three considerations kind of led me to think about, I really like working with long context models, and it's absolutely going to be the continuing thing. But are there retrieval strategies that are lightweight, easy to use with long context models that kind of preserve the ability to utilize a lot of context, but can address some of these limitations? In particular, this last piece was important because this is something I want to do kind of in the near term. And I need kind of like a nice lightweight retrieval strategy that still uses long context, but can operate in cases where my documents are maybe just a little bit bigger than my context window. In this case, like around 2x. So I kind of put this out on Twitter and said, hey, has anyone come across good, maybe minimalist splitting strategies for long context LLMs? I want to do RAG with Mistral 7B with a 32,000 token context window, but my docs are 60,000 tokens. I can't just context stuff them, but I also don't want some very fine scale chunking thing. I get it. We don't want to mess with all that. We want something simple that just can kind of work across larger documents. So one point that was raised, which is a really good one, is, just index at the document level. So you can take full documents and just embed them directly. It's a fair point. And then you do something like KNN on those embedded documents. So again, no chunking of any documents, no splitting of documents. You have your set of documents, embed each one, and just retrieve at the document level. That's a pretty good idea. That's pretty reasonable. Another idea that came up, though, is this idea of building a document tree. And part of the reason for that is when you talk about something like KNN or K nearest neighbor retrieval on a set of embedded documents, it is true that sometimes an answer requires maybe 2 or 3 different documents kind of integrated in order to answer it. Now, if you context stuff everything, that's not a problem. because it's all there. If you're doing retrieval, well, you're setting your K parameter to be some value. It's kind of brittle. Do you need to be like 4 or 5 or 6 to capture all the context needed for certain particular questions? So it's kind of hard to set that. So this idea of building a document tree is kind of an interesting way to potentially address this challenge with like basic KNN. So a paper, Raptor, came out recently on this exact idea. And their code recently open sourced, which led the folks at Llama Index to come out with a Llama pack for it, which is great. And the idea is pretty interesting. So I wanted to kind of lay it out here and talk about how it might benefit this exact case of kind of long context retrieval. So the intuition is pretty simple. First, we take a set of documents. Now note that these documents can be any sized. So in their case, they're just chunks. So they're like 100 tokens. But it doesn't matter. So we start with a set of raw documents. Now what we do is we embed them, and then we cluster them. So this clustering process groups together like documents, and then we do one important thing. We summarize information in that cluster into what we call kind of like a more abstract or higher level summary of that content. And we do that recursively until we end up with one cluster. That's it. So what's happening is you're starting with this set of what they call leaves or like raw documents. You do a grouping via clustering, you do a summarization steps, you're kind of compressing, and then you do it again. And the idea is that these kind of mid-level or eventually like root level or highest level summaries can consolidate information from different places in your documents. Now what they do is they basically just embed those summaries along with the raw leaves, and they perform retrieval. And we'll talk about that a little bit later, but what they show is actually just doing retrieval on all of these together, like as a whole pool, performs best. And that's kind of a nice result. It's pretty easy then to basically just index that and use it. I will make a note that their paper talked about these leaves being chunks, which I didn't love because look, I want to work with long context models and like I don't want to deal with chunking at all. And I replied to Jerry's tweet on this, and Jerry made a fair point that this can scale to anything. So for example, those leaves can be full documents. They don't have to be chunks. That's a completely reasonable point. So again, you can kind of think about this as if idea one was, let's just take each document and embed it. Idea two is, well, let's embed each document like we did, and we can also build kind of like a document abstraction tree on top and embed those. So we have these like higher level summaries in our embeddings, which we can retrieve from if we need an answer to contain information from like a small set of documents, right? So it's a little bit more robust maybe to this problem, which is that if I'm just doing KNN on raw documents and I need information from like 2 or 3 documents, I'm not guaranteed to always get that because of this K parameter that I set. I'm only retrieving K docs. Whereas here, I'm building these docs that contain information from multiple leaves or multiple, sub-docs, so to speak. And it can actually just capture that information in kind of a nice way, such that it can basically integrate information across different individual leaves or individual documents. So that's the key point. And so we can kind of see, when you think about like working long context models, of course, context stuffing is a great option if you can do it, but there are some other interesting ideas. One is actually just embedding full documents, and another is this idea of, again, documents and an abstraction tree. So let's go ahead and just build Raptor, because it's pretty interesting. And to do this, I'm actually going to look at Claude 3, which just came out today. It's a new set of models from Anthropic, really strong performance, and should be really good for this use case, because what I want to do is I want to perform summaries of individual documents, and I don't really want to worry about the size of those documents. So I'm going to use the same set of documents that I previously did with the code generation example. That video came out last week, and I have an empty notebook here. We just do a few pip installs. I'm setting a few environment variables for Langsmith, and now I'm just going to say grab my docs. So that's right here. And this is going to grab around 33 web pages of documentation for LangChain related to LangChain expression language. Okay. And what I'm going to plot here is a histogram of the token counts of every page. So a bunch are kind of small, that's fine and easy to work with, so less than 2,000 tokens. A few are pretty big, so up to like 12,000 tokens. So that kind of gives you a sense of the distribution of pages that we want to work with, and we're going to apply this approach to those pages. Now I'm going to use Anthropic's new model to do that, and I'll use OpenAI embeddings, so that's fine, I set those. And now what I'm going to do, so this code was released by the authors of the paper. And I'm going to explain how this works in a little bit. But for right now, I'm just going to copy this over. And this is all going to be accessible to you in the notebook that we're going to make public. So this is all the clustering code, and we're going to talk about what it's doing later. I added comments and doc strings to this, so it's a little bit more understandable. Here's some code that I wrote that basically is going to do, like, orchestrate the process of that cluster, summarize, and then like iteratively perform that until you end up with a single cluster. So there we go. I'm going to copy this code over, and I'm going to kick this process off, and then I'm going to walk through it while this is running. So that's running now. Now first I want to kind of explain how this clustering process works. It's kind of interesting. So the idea actually incorporates four important points. So it's using this GMM, this Gaussian mixture model, to model the distribution of the different clusters. So what's kind of cool about this approach is that you don't actually tell it, group the data into some number of clusters. Like you do with some other approaches, you kind of set the parameter you want, like n clusters. Here, it actually can kind of infer or determine the optimal number of clusters, and it uses this like BIC. Again, you can dig into this in more detail if you want, but the intuition is that this approach will kind of guess or attempt to determine the number of clusters automatically for you. And it's also modeling the distribution of your individual documents across the clusters. It uses this UMAP, or basically it's a dimensionality reduction approach to improve the clustering process. So if you want to like really read into this, that you should actually just go and do that. The intuition is that this actually helps improve clustering. It also does clustering, what they call like local and global. So it tries to analyze the data at two different scales, like kind of look at like patterns kind of within smaller groups and then like within the full data set to try to improve how you're going to group these documents together. And it applies thresholding to assign basically the group assignment for every document, or the cluster assignment for every document. So this is really the idea. Here's all my documents. Let's look at this one. What's happening is it's using this GMM to basically assign a probability that this document belongs to each one of our clusters. So like here's cluster 1, here's cluster 2, here's cluster 3. Each cluster will get a probability. And this thresholding then is applied to those probabilities such that a document can actually belong to more than one cluster. So that's actually really nice, because in a lot of other approaches, it's kind of mutually exclusive. So a document can only live in one or another cluster, but with this approach, it can actually belong to multiple clusters. So that's like a nice benefit of this approach. I think that's kind of all I want to say initially about this clustering strategy. But you should absolutely have a look at the paper, which I will also ensure that we link. So right now, let's actually go look at the code. So we can see that it's performing this cluster generation. And let's actually look at kind of what it's doing. So it really follows what we just talked about. We have a set of texts. And in this case, my texts are just those 33 web pages that I'm passing in. So we can actually look at that. So what I passed in these leaf text I define as my docs. Again, let's actually go back and look at our diagram so we can like follow along. Here we go. So these leaves are my web pages. That's it. So here's my leaf text, and you can see, let's look at the length there. Okay, there's 31 of them, so that's fine. And what's happening is those first get embedded as expected. And then, so here's the embeddings. And then they get clustered, and this perform clustering is taken directly from basically the results or the code provided by the authors of the paper. So it's doing that process I just talked about of clustering and basically cluster assignment. And we get our cluster labels out, we put those in a data frame. And so then we have our clusters, you can see that here. And because each document can belong to more than one cluster, we actually expand out the data frame so that the cluster column may contain duplicates for a single document. So one document can live in multiple clusters, and we just flatten it out to show that. Then all we do is we get the whole list of clusters here, define a summarization prompt, pretty simple. And all we do is we have our data frame, just fish out, give me all the texts within each cluster, and that's all we're doing here. For each cluster, get all the text, plumb it into our summarization prompt, generate the summary. Here's our summary data frame. That's really it. So again, iterate through our clusters, get the text for every cluster, summarize it, write that out to a data frame. And that's all we do. Here's our cluster data frame, here's our summary data frame from that function. And this is just orchestrating that process of like iteration. So we just keep doing this until I provide like a level or n levels parameters. You can say do this n times, or the number of clusters is equal to 1. So basically this is saying continue until either we've done n levels or like n number of attempts in our tree, or the number of clusters is 1, keep doing that, and that's it. So you can see we've actually run that process. We have our results here. And now what we can do is pretty simply, we can just put those into an index. Like we can use Chroma as a vector store. So here's just some really simple code to do that. We're just iterating through our results. We're getting all of our summaries out. So first, maybe I should make this a little bit more clear. We take all those raw documents and we add those to our text lists. We then get all of our summaries from our tree. We add those and we just index all of them. So let's do that. So these are going to all be added then to Chroma. And very finally, we can set up a retrieval chain that is using this index, which contains both our leafs, so all those raw web pages, and these higher level summary pages. That's all that's happening here. We pull in a RAG prompt. Here's our retriever. Here's our question. So let's give this a shot. So this is running. And I want to just bring you back to the diagram so again, you can kind of see what's going on here. Right here. So again, we took our web pages, again, 31 of them, we clustered them, we summarized them, we do that iteratively. Then what we do is we take those summaries that we generated along with the raw web pages and we index all of them. That's it. And we can use that index for retrieval. So this is like a nice, what we might call a long context index, because it contains just raw web pages, which vary from 2,000 to 12,000 tokens. And it contains, in our case, these higher level summaries in case we need an integration of information across those pages, which may or may not be captured just using KNN retrieval. So that's the big idea. Okay, this ran, we got our answer. We can check Langsmith and we can see, here's our retriever. And let's see, here's the raw documents. So it looks like it retrieved some kind of higher level summaries as well as some raw leafs. So this is like a raw web page. And then some of these are more like summary pages, which looks like we produced. So what's kind of cool about this is you can retrieve from a combination of like your raw pages as well as these higher level summaries, which gives you some robustness and semantic coverage for different types of questions that require like different resolutions of abstraction or detailed answer. Like a really detailed code question, you might retrieve directly from your raw pages, but like a higher level question that integrates information from a bunch of pages, you might retrieve from these mid-level or even top-level summaries. So it's a cool approach. It integrates kind of nicely with long context models. And I know one thing that will come up here is, well, look, your full context was only 60,000 tokens. You could just stuff all of that into one of these models. You didn't need to do any of this. That is absolutely true for this case. But what I think the higher level point is, that's not true for every case. For example, this exact set of documents I want to use with Mistral. Mistral is only 32,000 tokens. So this is a really nice approach for that case where I can kind of guarantee that I can index across all these pages, but I won't exceed the context limit or am likely to exceed the context limit of my LLM because none of these individual pages exceed 32,000 tokens. So, you can see, and again, this scale is arbitrarily large, so it is true that this set of documents is only 62,000 tokens, but of course there's much larger corpuses which could extend beyond even the 200,000 of Claude 3, in which case this type of approach of kind of indexing across documents and building these like kind of mid-level, higher-level summaries can be applicable. So it's a cool method, it's a neat paper. I definitely encourage you to experiment with it. And all this code will be available for you to work with. And I think that's about it. Thanks very much.